Good morning, everybody in the lecture hall who wasn't scared of the snow. Good morning, everybody on Zoom. Good morning, everybody watching us from the future. Today, we will finish this part on the ecosystem of SQL, and in particular transactions, what happens when a lot of people use and access the database system at the same time. And then, if time permits, we'll continue with views and indices. Just to make you aware of something, there was an update in the somehow to the versions of Jupyter and what we use in there. And now there is an error. So basically, I will show you what happens. If you try to run it again, this is what you get. Basically, you get this key error default. All you need to do is to add that one line here, also put it on the Moodle. And if you add exactly that line, that solves the issue. Right? So the TA team will create a new Docker with that line added, but you don't need to wait for it. You can just add that line. You will find it in the Moodle forum. Somebody asked for it, right? Okay. So now, where is Zoom? Yes. Go back to where we were. So this is where we were. We basically are looking at a database system that is used by a bank. I would never be a customer of a bank implementing a system like that, right? This is just for illustration purposes. We have Alice and Bob who both try to access the database, and we saw that because they do their query kind of assuming they're the only ones connected, but actually there's somebody else, then that interferes, right? Who remembers this from last week? Because they both write a balance, and whoever wrote the last one actually wins. And so Alice surprisingly gets a 3,000 as a result of her query, which is surprising to her because she just put 2,000. So this is how she sees she's not the only one using the system. And so in order to study these things, there is a theory. And what we do is that we display the queries like this. So with every column corresponding to one user, right? So we have here, that's everything that Alice does is here, and everything that Bob does is here. Then we add these rows here that are called conflicts. So here it's called a read-write conflict because Alice reads before Bob writes to the same place. Then we have write-write conflicts. This is when Alice reads and then Alice writes something and then Bob writes at the same place. So that's write-write. And then we have write-read conflicts. This is when Bob writes something and then Alice reads it, right? So basically, what these rows mean is that the order is important. If you would swap the order of the two queries that you connect with these rows, then that would change, right? If you would swap, for example, the two writes, then if Alice does it second and Bob does it first, then they would both read 2,000 at the end, not 3,000, right? So this is what the arrows tell us. And so when you do that, you then abstract away, and here you get a graph. Who knows graph theory? Right? It's a whole area of mathematics where we have nodes and edges, and the edges connect nodes. Here it's a directed graphs because the edges connecting the nodes have a direction, right? It goes, for example, here from here to here. So here, this is a graph with 6 nodes and 1, 2, 3, 4, 5 edges, okay? So what happens is that we formalize this when we write it directly as text. We basically write top down, so time elapses like this, right? First this, then this, then this, then this, then this, then this. We write it like this, right? So this means Alice reads Albert Einstein, that's here. Bob reads Albert Einstein. Alice writes W to Albert Einstein. Then Bob writes to Albert Einstein. Then Alice reads Albert Einstein. Then Bob reads Albert Einstein, right? And you can go back and forth between the two. So if I give you that, you should be able to write this. And the other way around, if I give you this, you should be able to write that. Not the exact query, of course, because here we don't put the exact queries, but it only matters that they are reading or writing to the same thing. So this is what happens. And so in exercises, sometimes you can basically get a list like this of queries that people access, always with the different people accessing the database and what they are touching. Here is all the same field, but it doesn't have to be all the same. And then read or write. And so you should be able, if I give you this, to draw a graph like this, right? With the nodes and the edges. So for example, let's do it. So this is another example where we have Alice, Bob, and Charlie, right? We have 3 people, A, B, C. They read or write, R and W. And here they read and write to 2 places, alpha and beta, right? We call them alpha and beta. So we have 3 people that are writing at 2 places. So what we need to do in order to analyze this situation is to create 3 columns, because there are 3 people, 3 users, so 1 column per user. And then on every row, we put 1 query, only 1 per row, right? And we put it in the right column. So the first one is in column A, the second one is in column B, the third one is in column B, right? 1 per row every time. And every time you just write it in the column that corresponds to the subscript here, C, A, C, B. Who would be able to do that, right? So this is the what you do. So it's more visual, okay? You see what's going on. And then you need to find the read-write conflicts, the write-read conflicts, and the write-write conflicts. Can anybody give me examples of conflicts? Anything, read-write, write-read, write-write, any examples? The arrows that I can put in there. Yes? Between, sorry? The first and the second entry. We are going to try to use the microphone too so that we can hear you on Zoom, but you basically said between these 2. And indeed, this is the same location, alpha. So they are looking at the same location. And this is a read-write conflict, right? So indeed, we could have an arrow here. Another one. Can anybody tell me another one? Yes? The 5th, this one? And the last, yes, this is both beta, and this is a read-write conflict. Anybody else? Does anybody see a write-write conflict? The second and the 4th, yes, this is a write-write conflict, right? It's alpha and alpha. You always need to check that it's the same one, and here it's the same one. So that's a write-write conflict. Do we have any write-read conflicts? The 4th and the 7th, this one. Yes, indeed. This is alpha and alpha, so that's the same. Exactly, right? So to have a conflict, you basically need to be looking at the same data, and it needs to be 2 different people, right? And it has to be at least one right. There is no such thing as a read-read conflict. If it's read and read, then there's no conflict, right? So it's always read-write, write-read, or write-write. So these are indeed, you found a lot of them. So these are all of them, right? This is, I think, everything that there is to be found here. Okay. Oh, no, that's not everything. That's even more, even more. Now we have everything, right? So this is the sort of things you need to do. You need to basically write all the conflicts that you see in there. So now where are we doing that? I'm coming back to the former example here with just Alice and Bob looking at one place. The question here that we are asking is, can we disentangle the spaghetti, but without hurting the arrows? Basically means, can we disentangle things so that Alice has all her queries first and Bob has all the queries after that, or the opposite, first Bob and then Alice, without any entanglement? And the idea is that here we cannot. And what you need to see is that if we were able to kind of rearrange, push up and down basically these queries in such a way that we would bring everything Alice, then everything Bob, or everything Bob, everything Alice, without swapping the arrows. Because of this arrow here, it would have to be Alice first and then Bob, right? Because we have a constraint that Alice must be first and then Bob. The problem is that we also have an arrow here from Bob to Alice, meaning it needs to be Bob first and then Alice second. So we have what's called the cycle. We have to have Alice first and Bob second, but we also need to have Bob before Alice, right? So that is unsolvable. You cannot order Bob and Alice in a way that Alice is before Bob and Bob is before Alice. That is a cycle. What is the magic that happened between this slide and that slide? So what we did is that we took all of these nodes of Alice and we just merged them into one, right? Merging also the arrows. Then we took all of Bob's arrows and we just nodes and we merged them like this, right? And then we have an arrow between the two whenever there is at least one from somewhere here to somewhere there. To whom is that clear? Right? So I squeeze this, and I get this, right? And so here you see there is a cycle. That's called the cycle in graph theory. And that means that in that case, we cannot do anything about it. The spaghetti is entangled and we cannot disentangle it. Now, here's another example. It's something different. It's not the same schedule as before. You see, I changed the order in there. But this schedule, so by the way, this is called the schedule. All of these things that you see up there, the line of text here is called the schedule, right? This is basically a list of transactions that people do to a database. This is called the schedule. And so if we take that schedule here, what you can see is that everything here is Alice, and then everything here is Bob. This is special. That doesn't always happen. But if you would plot it as a graph, you would have Alice, 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 and then Bob, 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 right? That is called a serial schedule. It is called a serial schedule because you can order the people. It's first Alice and then Bob. And there's never Bob before Alice. So this is called a serial schedule. Now, I think the next slide is going to do something. I have that slide that basically says, yes, if you now squeeze this together and squeeze this together, you will only get from Alice to Bob. There is no arrow ever that goes from the right to the left. That doesn't exist, right? It's always Alice to Bob. So here, if you would squeeze them, you would get a graph with two nodes and an arrow from Alice to Bob. So there's no cycle. Of course, it's serial, right? So we know that it works. Now, how does it work in practice if they are actually connected to PostgreSQL and they're actually executing these transactions? What Alice and Bob will do is they will add special SQL instructions. At the very beginning, Alice is going to write begin semicolon, and then she will send her queries and then commit semicolon to say, I'm done. Committing means you now save that all and persist these changes forever. Bob is also going to do the same. He puts a begin, then the queries, and then commit, right? This we haven't seen before, this begin and this commit. What that means when you put a begin and a commit is that the SQL queries that you write, some of them updating, belong together. They form a unit. And by putting the begin and the commit, you signal that you would be worried if it interferes with other people. So you want to tell PostgreSQL, these queries belong together, be careful, do not let it interfere with other people. So in that case, if we would execute it in that way, we are respecting the wishes of Alice and Bob because, you know, PostgreSQL would first execute everything by Alice, and then PostgreSQL executes everything by Bob. So here we respected the wishes of Alice and Bob that they expressed via begin and commit. To whom does that make sense? Right? So now it's trivial, right? Whenever people write begin and commit in their SQL queries, we just pick one at a time and we let everybody else wait, right? That's how we implement it if we want to respect their wishes, right? So we just let them queue and we do them one by one. Now imagine that you would book your train ticket and that would be like this, like SBB tells you, please wait like 1,200 other customers because we are taking care of Hans Muster first, and then we'll do one after each other nationally. On the national level, people queue. That wouldn't work, right? And it's exactly for that reason that the engineers that designed these systems tried to tweak it in such a way that we do not actually execute it in that order. So we would actually execute them at the same time, but very smartly in such a way that people would believe that they are actually alone and that everybody's queuing. It's only pretending. Do you see an easy way that I could actually start Bob's query before Alice is done without them noticing anything? Does anybody see it here? Could I already start dealing with Bob before Alice is done? I see 2 raised hands, yes? Like this? Yeah, exactly. This is the trick. So absolutely a correct answer. Indeed, if actually PostgreSQL, upon receiving these 2 transactions, would say, okay, let me start with Alice. I'm executing this, and then let me already start dealing with Bob, even though I'm not quite done with Alice, but let me start with Bob. So you do that, and then you finish with Alice, and then you continue with Bob. This is a bit more efficient because now it's a bit, at the same time. So you can basically finish earlier, right? Who sees that it's the same? Why is it the same? Would it always work? Yes? Exactly, it's read-read. There is no conflict between the two. In that case, because it's read-read, there could also be other reasons why it's not a conflict, right? It could be that they are not looking at the same data. It could also have been that here it's for Albert and here it's for Mariam, right? So it's not the same. So there is no conflict. There is no arrow between these two right here. And whenever there is no arrow, we are free to push up and down these things, right? It makes me think, I don't know if anybody knows Stargate with the rings when the Goa'uld arrive on a pyramid, but pushing this up and down reminds me of these rings, if anybody knows the reference. But it's like a game, you need to rearrange. And so if you look at it conversely, if I would give you that schedule where you see I swapped these 2, I can ask the question in the opposite way. If I give you this, can you push it up and down so as to disentangle it? And here the answer is yes, you can push it like this. And when that happens, when you can push it up and down in such a way that you obtain a serial schedule, meaning it's as if people were queuing, then we call it serializable. Serializable means it's not necessarily serial, but you can rearrange it and push it up and down in such a way that you can make it serial. The only hard constraint is do not ever push it up and down across arrows. For example, here, you cannot push it up and down here because there's an arrow. The arrows constrain the way you can push up and down. For whom is that clear? Right? So this is called a serializable schedule. And so a common question that gets asked in database textbooks and in exam is, if I give you a schedule, is it serializable? And now you know the algorithm. If I give you a schedule, what you do is that you basically put it in a table like this. You find all the conflicts. Then you squeeze all of that. Oops, what am I doing? You squeeze all of that, and all of that, and then you look for cycles. And if there is a cycle, then you cannot. It's not serializable. If there is no cycle, then it is serializable. So let me go back to where we were. So if you take that example here, where it is not serial, how can we tell it's serializable? Because there are only arrows from the left to the right. You will not find a single arrow that goes from the right to the left, right? So if you squeeze that and squeeze that, you will only have an arrow from the left to the right. There is no cycle. And thus, you can say, because there is no cycle, it is serializable. That's how it works. Now, this is another one that's a schedule. And I'm asking the question, is it serializable? Why is it not serializable? Can anybody see it? Yes? Exactly. So we have, let me show at the same time that you explain. So you said there is a write-read conflict. Do you mean, for example, from here to here? Yeah. So that is from Alice to Bob. And there is at the same time from Bob to Alice, right? So basically, that means that you can try to push up and down all you want, but you will have this entanglement here with the spaghetti so that you can push up, that's fine. But now you're stuck, you cannot push that up because of this. And you can also not push that down. So this is basically entangled, right? The best you can do is arrange the reads right here. You can rearrange a bit, but here you're stuck. So there is no way you can disentangle that. And the way you can tell is that if you squeeze them together, you have arrows that go from Alice to Bob, and you have arrows that go from Bob to Alice. So this is what you get. There is a cycle. For this reason, because you cannot rearrange up and down to disentangle it, it is not a serializable schedule, right? You can convert it to these different schedules. They're called conflict equivalent schedules. It means all of these are the same, right? But you will never be able to find something that is the same and that is serial, right? So that's the idea. So we say it is non-serializable. The spaghetti is entangled here. What about this one? Can anybody find out if this is serializable or non-serializable? Non-serializable. What does everybody think? Who thinks it's non-serializable? Who thinks it's serializable? Okay, so now can anybody tell me why it's non-serializable? Yes, exactly. You have, so basically, a trick for looking at these arrows. After you have drawn the arrows, you don't need to look at these anymore. You don't care if it's alpha, blah, blah, blah. You don't care anymore. You just look at the arrows. And so basically, if you look at the arrows, you see that you have arrows that go from B to C and arrows that go from C to B. I assume this is what you just meant, right? There are arrows that go, if you take B and C, here it goes from B to C, and here it goes from C to B. That's a cycle. Then you have here an arrow that goes from A to B, and another one from B to A. This is so broken. It's like everywhere, there's cycles everywhere. You have from A to C, and you have from C to A. So it's a no-go, right? You cannot serialize it. So if you would squeeze this, and squeeze this, you would get this. Like this is the maximum graph you get, basically. There's arrows everywhere. So you see, there's cycles all over the place here. There's a cycle here, there's a cycle here, there's a cycle here, there's even a cycle here, and there's even a cycle here, right? So there's cycles everywhere. A cycle means you can follow the arrows and then go back to the same place where you were, just by following the arrows. For whom does that make sense? Right? So this has cycles, and as a consequence, the schedule that is up there is not serializable. You cannot rearrange it pushing up and down in such a way that you have an order between Alice, Bob, and Charlie. Right? Mm-hmm. We already considered that when we put the arrows. We only put arrows when it was alpha, alpha, or beta, beta. We didn't put an arrow if it was alpha and beta or beta and alpha. So we only put arrows if it was really the same data. Does it make sense? For example, there is no arrow between these two because that's alpha and beta. So we did not put an arrow here. So that means this we can rearrange. So this we could push, we could actually push this all the way up, this one, before the alpha without any problem because it's beta and alpha, it's different. Yeah, then don't hesitate to ask offline, right? So basically, I repeat the steps. You take the schedule, you arrange it in a table, one transaction, one query per row, putting it in the right column of the user that does the transaction. Then you put in the arrows, read, write, write, read, write, write, only if it's the same variable, alpha to alpha, beta to beta. And then you squeeze Alice, squeeze Bob, and squeeze Charlie, and then you get a graph with 3 nodes, and then you look at whether there are cycles or not. And here, there are cycles. Right? Who is with me? Well, very good. So there's plenty of exercises, and also in past exams, you might find some of them. Now, how does it look like to people actually using SQL, programming SQL? We have a question.
Yes. So the color of the arrows does not matter for the analysis of serializability. I think it's...
You're absolutely correct. It doesn't matter. I only put them for pedagogical purposes to tell you this is read-write, this is write-write, this is write-read. But it doesn't matter for the cycles. You don't care. I could have put them all in the same color and then continue. That would have worked too, right? Thanks for asking. All right. So now, what's new to SQL? I already taught you SQL with the queries, select from where, insert, delete, and so on. So that you all know. What is new is this begin and this commit. So you really are now in a situation that you are connected to the SQL server. It could be a Jupyter notebook, but now I explained last week that it could be in a computer program. That could be in Python or in Java or in PHP that you actually execute these SQL queries, right? So there is some host language. And so in that host language, you have this instruction begin that signals that you're about to execute multiple queries that belong together, that form a transaction. And you conclude that by committing. But in some cases, something goes wrong. Something goes wrong. And so you change your mind. Again, it's a computer program. So the computer program is starting to do a transaction like this, starting, updating, and so on. And maybe here you see something is wrong. Then instead of commit, you say roll back. That is a different instruction. Roll back means I change my mind, just forget everything and as if nothing happens. So it means that even after executing these ones, you're asking PostgreSQL to just revert all of that and do as if you never even did it in the first place. So begin commit or begin rollback. These are the two alternatives. Okay. Now you can tell PostgreSQL. I told you that when you say begin and commit, you're basically asking PostgreSQL to give you guarantees. You want to be protected against interferences with other people who are also booking a train ticket. And so you can express more detailed wishes. You can tell PostgreSQL what kind of isolation you need, right? Do you want maximum isolation? You want to be absolutely certain that it's as if you were the only one and everybody was queuing and waiting. Or you're telling PostgreSQL, you know, I'm fine if there's a bit of interference, right? And so you can set the guarantee level that you desire. You can say, I don't care about anything, or you can say, I care maximally. And so that you do with set transaction isolation level, and you have several of them. So these are the ones you have. You have read uncommitted, read committed, repeatable read, and serializable. And this is really a wish. You're telling PostgreSQL what is okay and what is not okay for you. For example, the risk of dirty reads. Dirty reads is you see some value that was put by somebody else, and it's not even committed. They did not even commit their transaction. So this is what we call a dirty read. And so in most systems, read uncommitted, if you say set transaction isolation level, read uncommitted, what you're telling PostgreSQL or the database system is, I don't care about dirty reads. And that's fine. So this is what you're telling to the system. In most systems, you could thus have dirty reads. But in fact, in the case of PostgreSQL, this is why I put two checks in there. PostgreSQL is kind of nice. They will not have dirty reads even if you say I'm fine. It simplifies a bit the implementation. So even though you can use, because that's the SQL standard, you can say read uncommitted. But even if you say that, you don't need to be worried. In PostgreSQL, you're not going to get dirty reads anyway. The next level is set transaction level, read committed. That means you don't want any dirty reads, but you're fine if you see something that was committed by somebody else. And if you still see the same, if you repeat the read, if you read it 2 times, 3 times, 4 times, you should still see the same value, right? And so that is that would be the repeatable read, the third one. And then you have serializable. that means it's as if everybody was queuing and there was one person at a time taking turns, right? And so if you look at the checks here, what you have is everything that can and cannot happen. So the maximum security is serializable. Then you're telling PostgreSQL, I want none of this. I want the absolute guarantee. It's as if I were the only one at the same time. Set transaction level read committed. You're saying, I don't want dirty read, but I'm fine if there's non-repeatable reads. I'm fine if there's phantom reads, or I'm fine if there's a serialization anomaly. Serialization anomaly means that it's not like you take turns. Serialization anomaly means you notice that you're not actually taking turns. That's what it means. Repeatable read means you're fine with dirty reads. You're fine with non-repeatable reads. You're fine with phantom reads, but again, PostgreSQL will never do that to you. So again, it simplifies the implementation. So even though the standard says you could have phantom reads, then PostgreSQL wouldn't give any phantom reads to you. And then here you don't care about serialization anomaly. Right. It's a bit complex because this is a 4x4 matrix that is technically not exactly symmetric, so it hurts a bit. This gives a bit of headache. But basically what you need to remember is that this is the less, like you don't care so much, and the more you care about the guarantees you want, the more you go down, right? The safest is this one, right? If you don't say anything, it's going to assume that you want read committed. All you want is to not see any dirty reads, but you're fine if the others happen. Okay. For whom does that make sense? Okay. By the way, I don't know if you remember, but these 4 here, I told you about last week, right? There were slides on that, right? I can say it again just for reference. A dirty read is if you can see a value that was written by somebody else before it was even committed. That's a dirty read. Non-repeatable reads, it means you see a value somebody else committed, but if you read it again, it has changed, meaning that you see that the value actually changes. So you notice you're not the only one. That's a non-repeatable read. Phantom read means even though when you read the same thing repeatedly, you always see the same value, you might see new records that appear out of nowhere. So you also notice that some people are using the system as well. So that's called the phantom read. It's when you see new records. And serialization anomaly means you notice you're not taking turns, right? It cannot pretend that everybody's taking turn and executing one after the other, right? And the more you go from the left to the right, the higher the guarantee, the more difficult it is to implement. For whom does that make sense? Who is lost? Not lost. Okay, very good. Okay, this is already advanced, by the way, right? So that's an example where you ask for repeatable read. So you want to make sure that if you read the same value multiple times, it will always be the same value. But you're fine if you see a new record appear out of nowhere, or you're fine if you see you're not taking turns. Right. Now, how does PostgreSQL actually do it? Because it's not so easy to implement these things. There's 2 paradigms in databases, in database systems to implement transactions and these isolation levels. The first paradigm is based on a locking mechanism. What is a lock? It basically means Alice starts querying, she starts sending her queries, and she locks down the entire database to herself for the moment she executes her query. When she's done, she removes the lock and other people can use it. That's called the lock, right? So the lock can be at the level of the whole database. It can be at the level of a row. You lock a row for yourself to modify it and nobody else can touch it at the same time. Then you unlock it. This is called the locking mechanism. For whom does that make sense? Right? So locking mechanisms exist as soon as you have concurrency in operating systems. So this is one way. But there is another way. In fact, this is what PostgreSQL does. This is a versioning mechanism. A versioning mechanism, who is familiar with Git? It's basically Git. It's the idea that whenever you modify the table or you add a new row or you modify a value, in fact, you're just creating a new version of the database. The former version is still there, just has an older version number, but every time you make an update, you create a new version. And with a versioning mechanism, you can simulate these things. Because, for example, a repeatable read, if you want to guarantee somebody that they will always see the same value, imagine you're at version 3 and somebody is reading values at version 3. And then in the meantime, somebody else is modifying the values. So you have version 4, version 5, version 6, and the values has evolved. How do you guarantee to the former user that had read at version 3 and they don't want to see the values change? Well, you keep them on version 3. That's all you do. You just continue to deliver the results of the query as of version 3, and you just ignore the newer versions. For whom is that clear? Right? So this is Git. It's really Git. Like if somebody doesn't want to see other changes, they just branch and they have a specific version, and other people can commit to other branches. They don't care, right? Even though in that case, we don't even have branches. It's a linear versioning system, just 1, 2, 3, and so on. All right. So that's it. Locking, versioning. These are the two ways. And that's even my last slide, I think, of the. Oh no, that wasn't the last slide. There's one more thing. The one more thing is that in practice, so this is kind of the tips and tricks. Imagine, let me tell you an anti-pattern. Somebody who is using PostgreSQL or a database system the wrong way. You want to break it, basically. So what you're going to do is you're going to create transactions that have like 1,000 queries in there, 1,000 queries. Each transaction has 1,000 queries. You're going to require the maximum isolation level for these transactions with 1,000 queries, meaning you want to be as if you're the only one in the database executing these 1,000 queries as if you were alone. And on top of that, you're throwing millions of these at PostgreSQL. So millions of very large transactions with maximum isolation level. This is going to kill the system because this puts so much requirements on PostgreSQL that it doesn't work. So that was an anti-pattern. What does it mean in practice? You should try to keep the number of transactions a small number as a person, not too many transactions. You should try to keep that small, not too many queries in there, because every time you add more queries, again, you're asking more from the system. And you should also keep your transaction active. What I mean with that is that, so let me go back to the anti-pattern. So imagine you connect to the SBB train system. You build a transaction, maximum isolation level, with 1,000 queries that take all of the seats of the train, and then you just go away for a month without committing. Everybody's blocked, nobody can use the system. This is what I mean with active. Active means when you start a transaction with begin, do not wait too much until you finish, right? Do not keep it open like this forever. So it must be active, and you must commit within a reasonable amount of time, right? And then read-only, so what I mean here is you should specify your isolation level with reasonable request, meaning that do not always say maximum isolation level if you don't actually care. If you know you don't care about phantom reads or you don't care about repeatable reads, then just adjust your isolation level requirements to a lower level, right? Only put serializable if you really, really want that maximum isolation level, right? To whom does that make sense? Right? So these are a few tricks. So try to keep your transactions, few of them, small enough, active. Don't wait too much before committing. And if you can, then try to specify reasonable transaction isolation levels. There is something I forgot to say, and I realized why I write read-only. There is another reason, but it has to do also with being reasonable with the requirements. Maybe I can go back to a few slides. Just one last thing that I forgot to tell you. Do I have it here? Oh, maybe I didn't have it on my slides. Did I put? No, I didn't put it on my slides. When you have this set transaction isolation level, there is something else that you can do. You can say that you're only reading from the database. You're not writing anything. That's a read-only access. And if you tell PostgreSQL that you're read-only, you're just reading data, that's easier for it to make the guarantees, right? So if you're not writing anything, you're not updating or deleting anything, all you want to do is read but you want some guarantees of repeatable reads or no phantom reads, then say that it's read-only. There is also an instruction for that. So this is what I mean here. If applicable, then read-only, right? Only request the guarantees that you really need. Okay, now I'm done with that part. Who is with me? Okay. Very good. So what to keep in mind is always the example of booking tickets on a train or on a plane. This is basically the top example. The other one being transactions, like banking transactions. Actually, even in finance, the notion of settlement and so on, all of that is quite complex. So we have 5 minutes to the break. Any questions on the transactions? Okay. Then I'm going to wrap up on this one. I think I still have a bit of time to start the next one before the break. So let me stop the recording.